we're going to look at photons. Now we're going to start off by looking at what was called the ultraviolet catastrophe. And what was that? If you see this graph, this is the energy that was predicted by this Rayleigh-Jeans formula, which basically had this blue curve here. And it predicted that as the wavelength got shorter, in other words the frequency got higher, that we got this asymptotic graph towards the low wavelengths. So basically, as the wavelength decreases, the frequency increases and the intensity gets higher and higher and higher. In fact, it will go off to infinity. And there was a bit of a problem with this because ultraviolet shouldn't do that. They knew that ultraviolet would have lots of energy, but it basically didn't fit with what the observation was. And the observation basically departed at visible light. You had this sudden peak at 500 or so nanometers. There was this peak at 500 nanometers, and then the value went down. It didn't follow what was expected. The new ultraviolet had a lot of energy, but all of a sudden it went down to zero. They knew that ultraviolet had lots of energy, but it didn't produce much energy, so they couldn't understand why. It didn't fit the model that they had at the time. In fact, it peaked at around 500 nanometers, and then went down. So, in fact, even though they understood that ultraviolet had a lot of energy, it didn't actually contribute much to the intensity. And they didn't understand why. Until this guy came along, Planck, and he explained why ultraviolet light, in fact all light, behaved in this strange way. He said that the ultraviolet does have more energy, but this energy comes in packets, and the energy of the packet depends on the frequency. And the equation is E is equal to hf. H is Planck's constant. Now, the reason they had so much low intensity is because to bring the energy, there are fewer and fewer packets of energy. So, ultraviolet has more energy, but it comes in these packets, and as you've got less and less energy, there are fewer and fewer packets. These packets were called quanta, or called photons, these packets of light energy. And the energy of one quantum is h times by f. So it depends on the frequency. Now the lower intensity of this graph, basically because there are fewer packets that were bringing this energy. So light comes in packets. Light is quantized. It has certain values which depend on the frequency. Planck's constant is around 6.63 times 10 to the negative 34 meters squared kilograms per second. Let's look at an example of this. What is the photon energy of violet light, which has a wavelength of around 400 nanometers? We apply the equation E is equal to hf. We know h, but we don't know f. And we're talking about light, so we know that the speed is equal to f times lambda, v is equal to f lambda. And we substitute that value into the E is equal to hf equation. So it's hc divided by lambda. We'll substitute the values. And we end up with an answer of around 5 times 10 to the negative 19 joules. It's a very small amount of energy in a photon of light. A more useful unit would be to find this in electron volts. So we divide by 1.6 times 10 to the negative 19 to give the energy in electron volts. So it will be around 3.1 electron volts. Here we have a table showing different colours of light, what their wavelengths are, and what the photon energy is. So you see violet has a high photon energy, red has a smaller photon energy.